Right, I wanted to make a quick video about the antiderivative of 1 over x. And so just to put things in context, the problem we might be solving, we might try to find the antiderivative of this function 3 plus x cubed plus 1 over x. And we learned some rules, right? We learned that, of course, what has derivative 3? It's going to be 3x. What's going to have derivative x cubed? Well, we should increase the exponent so the 3 goes up to a 4. And then we divide by 4 in the front so that when we use the power rule, those 4's will cancel. And then we have, we learned a rule that the antiderivative of 1 over x is the natural log of absolute value of x. And then, of course, we add a constant because we can add any constant and it won't affect the derivative. And so today I want to focus on why is this absolute value appearing? So why is the antiderivative of 1 over x, why is it equal to the natural log of absolute value of x plus c? And why isn't it just the natural log of x plus c? So the answer is that it's not anything major, it's just that it's a slightly more general answer. So let's go to a graphing calculator and see how that works. So if we graph natural log of x, we have this nice graph here. Let me put it on projector mode. And if we want to compute, say, the slope of the tangent line, well, we can have Desmos do that for us. So if we have f of x equals this, and then we do f prime of x, right, Desmos is going to graph this. This shows us that our derivative is getting smaller and smaller. That's because our slope is getting smaller and smaller. The slope is really steep at the beginning, but then it flattens out. And if we wanted to check, if we look at the function 1 over x, sure enough, we can sort of see that it's exactly the same as our derivative, with one big exception. Since our function's only defined for positive values, our function log of x, we can't talk about the slope of the tangent line for any negative numbers. And that's fine. That's a property of the logarithm. It only makes sense to define it for positive numbers. But if we look at the graph of 1 over x, right, 1 over x makes sense for negative numbers too. And so if our goal is to say, well, what's a function that has derivative 1 over x, it seems reasonable that we should want a function that has that's defined and has domain that includes negative numbers. And so one way we could do that is we could say, instead of looking at the function log of x, well, let's agree to take the log of absolute value of x. Right, now all this does is say, well, it's the same rule as before if x is positive, but if x is negative, well, take the absolute value first. And so really we're just reflecting this graph over the y-axis. And if you think about what's happening, well, let's say the slope at this point is going to be exactly the same, but just the negative of the slope at this point. Right? This one's going to be going downhill, so it's going to be negative. This one's going uphill, so it's going to be positive. And so now if we were to graph the derivative of this function, we see that it will include positive and it will encode slopes for positive and negative values of x. And so, of course, we can check that it's exactly the same as the graph of 1 over x. So that's what's going on with the antiderivative of 1 over x. It's just that putting that absolute value in gives us a little bit more flexibility with our function. So thank you for watching. Bye.